I should have had the... Okay, so first let's just describe the application. See if this works. Great. Okay, so recall the inverse Galois problem. It's a pretty basic question. It just does every finite group occur as a Galois group of an extension of Q? And the hard part is saying Q. You pin Q down. It's a pretty hard question. I don't want to say what's been done, but it's hard. It's still very open. And a lot of partial progress has been made, mostly just fixing very specific groups and studying them. And in that spirit, a natural set of groups to consider is the simple groups. Okay, so as a student, these are the first simple groups you would learn. Cyclic group of order P, and it does occur. In particular, you can take your field K to lie inside the P squared roots of unity. The next group you would learn as a student would be the alternating groups, and that's due to Hilbert, his irreducibility theorem, and that's in the 1890s. And what I want to discuss is maybe the next class of simple groups you might learn as a student, and that's the groups PSL2FP, and they're simple with P greater than 5. And my application today is that all these groups occur as Galois groups for P sufficiently large. Okay. Previously, this was known if 2, 3, 5, or 7 was a square mod P. This is good, but this excludes a positive density of primes, and this one says I can exclude finitely many primes. And this theorem is known for if I replace this group with G2 or E8 more recently, but this is the first of the classical groups I can stick in here. Okay, so that's our application. And how we're going to construct it is we are going to study the Galois action on a tau cohomology groups of a specific surface. Okay? So the first goal, first order of business, is just to describe the surface. Okay? And it's really explicit. Okay, so there it is. Don't worry about everything at the moment. Main thing is that we have this nice equation, a Weierstrass equation. And how you should think of this is you have a number t, you plug it into that equation, and that defines a plane curve. Assuming you don't plug in 0, 1, or -1, you'll get a smooth plane curve. And as you vary t, you get these curves, and they give a fibration, which becomes a surface. And that's kind of all I'm saying here. I have this fibration away from these bad points at infinity, and the inverse image is this nice plane curve here. And I'm taking the projective closure, so it's a projective curve. And then I can fatten it up a little bit. I can extend it so it's well defined over these singular fibers. So you can take it so that the surface is smooth and projective, and this extension is relatively minimal, just meaning if you had another such extension where x is smooth and projective, it would factor through this one. Okay? You don't really have to remember things. You just have to remember there is a surface defined over Q, and there's some explicit equation it's coming from.
What you could write?
What, pardon?
What you could invent?
Oh, did I?
Usually when that extreme fixed and constant.
Oh, I guess it's not short Weierstrass. Is that the question, or? Oh, sorry. What?
Weierstrass was going for a small extreme plus 3 to.
Oh, okay, yeah. Yeah, okay. You could put a 4 if you want. Okay, so that's my surface. Now let me consider the representations. So we're going to fix a prime L, and for historical reasons, we're going to choose L instead of P. And we have this a tau cohomology group, so it's a surface. So the interesting cohomology group is H2. It's going to have coefficients in the L roots of unity. And since this surface is defined over Q, well, it's an FL vector space, but since it's defined over Q, we actually have a nice action of the absolute Galois group on it. Okay, and that's the nice thing about a tau cohomology. You get this extra Galois action. Okay? So it turns out this isn't really the thing we're interested in. We're only interested in a piece of it. So this is the interesting cohomology group. Now we're looking at the interesting piece. And there's a unique 4-dimensional subspace, which is also defined under the Galois action, such that the quotient, when you mod out by this interesting one, is trivial. So it turns out this cohomology group, I think it was a 34-dimensional vector space. but only a 4-dimensional piece of any interest. So you get rid of the boring stuff, and you're left with a 4-dimensional thing with an interesting Galois action.
So you take orthogonal of some algebra X.
Yeah, so you'd have a divisor class map in, and you would take all the fibers you know, and you take the orthogonal complement, and that's the VL. Okay? And you can describe the Galois action on this vector space VL in terms of a Galois representation. That's just a nice way to write that action. Okay, so that's our representation. The next thing is I have to explain why PSL2, because that's a 4-dimensional vector space. So next question, why PSL2? So we have our representation from the previous slide. And as you said, there is a pairing on the vector space coming from the cup product on H2. And it turns out the group lies in a smaller space, all the automorphisms that preserve this pairing. So the Galois group shrinks. And it's actually a little bit smaller. So I define a group omega, and that's going to be the commutator subgroup of our orthogonal group. And the claim is it actually lies inside this smaller group. Okay. So let's just assume the claim for a second, and I'll show where PSL2 comes from. So first we have our representation, and by the claim it lies in this smaller group. This group actually contains negative identity, so I quotient out. And then there's one of these, I'll call it an accidental isomorphism, sort of these coincidence with Lie theory of low rank. And it turns out it has a nice isomorphism with PSL2 cross PSL2. Okay, so this would be, maybe in terms of quadratic forms, this is dimension 4 in the split case. Okay?
We have to prove it is.
This is all, yeah, you'd have to prove it was split. It's not automatic. Okay, so we have this image, and then you can quotient down onto one of the factors. It turns out only one of the factors is any good, but I'll just leave it saying there's 2 choices. There's one actually which is better than the other one. And the theorem saying that PSL2 occurs as a Galois group is really saying that this representation from the absolute Galois group into PSL2 is surjective for sufficiently large L. That's the more general theorem than the one that was before. Okay, great. So at the beginning, I said I studied compatible families of Galois representations. So let me just tell you what compatible means. So compatible. So for each L, prime L, we have a representation. And it turns out if you take a prime P, there is a polynomial with rational coefficients such that if you look at, well, inside the absolute Galois group, for each P, there's an element like fraud P. It depends on choices, but the choices don't matter here. So you look at its image under rho L, and you take the characteristic polynomial, and it agrees this is only a mod L thing, so it agrees with our polynomial mod L. And what the compatibleness really means is that these polynomials don't depend on L. So we have these representations, rho L, and somehow they all know about these common polynomials P sub P. And that's just these representations all come from the same global object. Okay, so that's called compatibility. And yeah, these polynomials are important, and in fact, you can essentially recover the representations from them. Okay, so let me just, the rest of the time I just want to explain kind of why these polynomials are nice and how it has to do with the image. So here's our claim from before that the representation has a small image, whatever that group omega was, and this was our compatibility. And if you were to take an element inside omega, it actually always has the fact that the determinant of I plus the matrix is a square. And this is my little note here. It's the same as saying having trivial spinor norm, essentially. Okay, so if we apply it with the ones coming from, the matrices coming from this compatibility, by the claim, this is the claim here, they lie in the smaller group. So when I plug in, looks like I want to plug in t as -1, and then I get what I want. And I find that this polynomial, when I stick in the value -1, it is a square mod L.
Don't you need first to see that you're going to SO?
Yeah, so I'm skipping that part. I'm doing the harder part. Yeah, but you first have to show SO then omega. Exactly. Okay. And since this is holding for all L, we find that this is, well, most L at least, this is a square. Okay. And really how this works is you prove this, and then this is actually an ingredient to prove the claim. So let me briefly just mention this a little bit. So let's discuss our polynomial p sub p. And I'm writing down the same Weierstrass equation, except I've added a little twist by something. It's not important, but that's the exact same equation as before. And now I'm using it, but I'm looking at this mod p. So it's defining an elliptic curve over the field fp adjoin t. And associated to this elliptic curve, there's something called an L function. It's a series, but it's actually a polynomial, which encodes a lot of the arithmetic. And it turns out that our polynomials showing from our representation are L functions up to scaling the variable. Which is, I mean, it's not that surprising because it's the same kind of equations going on here. Okay, so our polynomials showing up were actually L functions. And what we were interested in is what happens when we plug in -1. Okay, so is that okay? So these polynomials, p sub p, are actually interesting. They're coming from L functions of elliptic curves over global function fields. So when we plug in, so there's same thing. When we plug in -1, we have this special value of an L function, which we're trying to show as a square. And this special value is a really important special value, because it's the one connected to the Birch-Swinnerton-Dyer conjecture. So here's a special case. If this special value is non-zero, and that's all I care about. If this is 0, it's a square. That's not the problem. So if it's non-zero, then it turns out that equation I had on the previous slide has only finitely many solutions, x and y, when I take x and y in this field fp adjoin t. Okay, so that's a special case of BSD. And it turns out, since we're in the function field world, there's an unconditional direction due to Tate. So knowing that this one value is non-zero actually tells you things about the elliptic curve. And actually, due to Tate and then Milne adding a little bit more, we have a more refined version. So if it's non-zero, we actually have a formula for it involving a whole mess of arithmetic invariants coming from the curve. Okay. So, questions? Okay, so again, this thing we're trying to show square is equal to a whole array of arithmetic invariants. This is the most mysterious thing. It's the Tate-Shevarevich group of our curve. And it's a finite group, finiteness being part of the implication of Tate. And once you know it's finite, its cardinality is this square. These CVs are things called Tamagawa numbers. They're pretty easy to compute, and I computed them. There's a power of p in the denominator. Again, it's pretty easy to compute. It's p squared. So we have our special value. It's the product of 4 things. All those 4 things are squares. So the value is a square. Okay. And then you said about getting into SO, that's just showing all the root numbers are 1. Okay, and 2 more slides. I don't want to explain anything about the proof of actually showing the image is big, but I'll just give an analogy. So this is something I like to study, Serre's open image theorem. So instead of surface, you start with an elliptic curve. You can study the Galois action on H1 for curves. H1 is the interesting cohomology group. And elliptic curves, this cohomology group is 2-dimensional. And a famous theorem of Serre is that this is surjective for L sufficiently large. And we're in a similar setting. For each L, we have one lying in PSL2FL, and we're trying to show it's surjective for L large enough. So my only point here is that this kind of looks like the same problem, right? PSL2 is not that different than GL2. So you take Serre's method as just sort of an outline, and then you try to generalize. Okay, and the last slide, just kind of things I want to work on. The first is I want to show that PSL2 occurs for all L. So I have to make the proof effective. I really want to say all L. That's the cleaner result. I want to give an effective version of Serre's theorem. I'm just writing it what it is here. Basically, I just want to write a program that computes things. I want to extend method to other simple groups. And these are some candidates. And one of the virtues of speaking last is I had an extra week and a half, so I actually proved it after I wrote the talk. And what I also want to do is construct some other simple groups. And the question mark is I've just run out of my own examples. So, say it again, where? Oh, these are, like this, let's just think about this one. Orthogonal group, dimension 2n plus 1, look at the FL points and take its, yeah, I'm just trying to match up with the one I have. Maybe you would write O, and this here, this would be O plus. Yeah. And finally, I'd like to construct other simple groups, but I'm out of examples, so if you have examples of where simple groups might be hiding, you should let me know. Oh, I mean, it's just we know the inverse Galois problem.
You don't take it like a
That's somebody else's. It's a different proof. I'm just saying this is the first kind of classical group where we know all L, not just L with congruences. Okay? So that's it. Thank you.
Thank you very much. Questions? Yeah.
you get into this kernel of the spinor norm. Is there some hope to lifting the representation to the spin group?
I don't know. Actually, I'm not sure. I think there might be an obstruction, but I can't say for sure. My representations, I don't think lift to SL2, for example. I'm not sure if I can lift, though. You would probably know that stuff. Yeah? It works for other groups, but sort of the challenge is simple groups. So if you just wanted the orthogonal group or the special orthogonal group, that's already known. The hard part is to get the simple group showing up. There's sort of methods called rigidity, which you can get orthogonal groups pretty easily.
Things like sporadic groups, right?
I mean, all but one of the sporadic groups are known just from rigidity methods, but they're not coming from any natural action.
And that's even over Q. That you don't need a secret.
Yeah, over Q, all but one of the sporadics are known. Yep.
Where did you get the equation of that surface from?
Yeah, that was most of the work, just computing. Basically, I needed that vector space to be four-dimensional, so it turns out I need an elliptic surface with very few singular fibers. Then I needed all the root numbers. I reverse engineered the proof. I sort of knew what I needed, and then I hunted. I needed all those values to be squares, so that was all thinking about BSD. So it was reverse engineered. I had the proof, and I just needed examples. But yeah, there's still just a lot of computer churning to find one that works.